This first part is going to focus on an introduction to alkynes and look at some common nomenclature rules. Alkynes are hydrocarbons that contain a carbon-carbon triple bond within them. The triple bond will react in many ways like we saw at the alkenes, but remember, how many degrees of unsaturation does a triple bond have? It has 2. So they can often undergo reactions multiple times. Also, if you have an alkyne where you have a terminal hydrogen at the end, meaning it's not flanked by 2 R groups, but maybe it's flanked by 1 R group and a hydrogen, that terminal hydrogen there is actually acidic. And so it will undergo a special class of reaction where we can use a base to deprotonate that hydrogen first and then react the subsequent product with something else. So those will be a new type of reaction that we'll see that are special to alkynes. But you'll notice that a lot of the reactants we'll look at when we're looking at addition reactions are similar reactants to the ones that you learned when we talked about alkenes. So if you understood the reactions that we did with alkenes and the reactants, you'll be seeing those again with alkynes. The triple bond of an alkyne, notice, is 180 degrees apart, and it's a linear molecule. So when you draw it, you have to draw it in this fashion. You cannot draw something like this. This is incorrect. So you have to show it being 180 degrees apart. Also, it's really hard to start counting carbons if you draw it incorrectly, because technically there's a carbon here and here. So by putting a kink in it, you're almost showing that there's a carbon there and a carbon there as well. So make sure that you draw your triple bonds using line bond structure like this. And then that would mean that there's a carbon here, here, and then here and here. The triple bond of an alkyne is made up of a sigma bond and 2 pi bonds. That's where those 2 degrees of unsaturation come from, the 2 pi bonds that are present. The hybridization of each of the carbons of an alkyne is sp hybridized, and we'll look at a little bit neater picture of the atomic and hybrid orbitals in a second. So here is our drawing of our atomic and our hybrid orbitals in the molecule C2H2, which is commonly called acetylene. That is a common name for the simplest alkyne that is present. So remember, we have unhybridized p orbitals that are present perpendicular to the inner nuclear axis. So here's our inner nuclear axis running through, and we have 2 unhybridized p orbitals on each of our carbon atoms. So there's a set there, and there's another set here and here. So that's where we get our 2 pi bonds from, is that sideways overlap of our unhybridized p orbitals. And running along the inner nuclear axis, we have sp overlap from this carbon with sp overlap from this carbon. That is where we get our sigma bond from, that direct overlap. The other bond that's shown is an sp overlapping with a 1s orbital on hydrogen, and then on the same thing on the other side, sp a hybrid orbital with a 1s atomic orbital on hydrogen, and those would both represent sigma bonds there because they're just single bonds. So our Lewis structure for acetylene would be hydrogen bonded to carbon, triple bonded to another carbon, and then bonded to hydrogen. Later, when we start learning reaction mechanisms for alkynes, we're going to want to compare it back to what you've already learned about alkenes and try to relate that to this new group of molecules. So a couple things to note. They both undergo addition reactions. They both have at least 1 degree of unsaturation. Alkynes have 2 degrees of unsaturation, whereas alkenes have 1 degree of unsaturation. But notice the electron density. This is where they differ a little bit. We saw that the pi bond of an alkene, so this would be the example on the right, something like ethylene, that it was planar. And so we could have attack from above or below that double bond. The electrons sit above and below the internuclear axis. And so where you see red, this is an electron density map. The red represents where there is high electron density. So if something's acting as a nucleophile, it's going to come from where that high electron density is. And so in an alkene, it's sitting above and below the plane of the molecule. Now notice how that's different for an alkyne, something like acetylene. So our electron potential map or electron density map, you can see that in an alkyne, there is a ring of electron density surrounding the entire triple bond. So no longer does the attack of the nucleophile, of the electrons, come from just above and below. It can attack from anywhere. And that's because of what we just saw on the previous slide, how you have two perpendicular pi bonds formed to the internuclear axis. So at each 90 degrees, you had a set of electrons there that are going to be free for attack. Looking at some general nomenclature, our suffix for alkynes is that they end in YNE or "ine". The general formula for a basic alkyne is going to be CN H2N minus 2. So we actually end up subtracting off 2 because of those 2 degrees of unsaturation. So you can figure out quickly the formula for any alkyne with a specific number of carbons in it. So for example, ethine, which the common name from the past is often called acetylene or acetylene, that is the same thing. And that's going to be our simplest alkyne that we can have with 2 carbons in it. So we're going to have essentially just this. So it's usually customary to show acidic hydrogens when they're at the end of an alkyne, even though in line bond structure we typically do not show hydrogens because this is considered a terminal alkyne where we have 1, 2 here. We do show the hydrogens. So showing this line bond structure, you would just have this. I know it looks a little funny at first, but you got to get used to recognizing that this means the same thing as this. And practice counting your carbons when you're drawing alkynes because it's easy to make a mistake when you're actually putting the correct number of carbons in just because it's a little weird to draw the triple bond in the beginning. So this would be carbon 1, this would be carbon 2. Moving up, F was 2, prop is 3. So 1 prop represents that the triple bond is going to be at position number 1. We'll go through all the nomenclature rules in just a second, but just the basics here. We're going to have our terminal hydrogen, and then this would be carbon 1, carbon 2, and so we need to have 1 more carbon. And remember, it's linear, so that next line coming off is going to be straight. So this would be carbon 3. I don't put a hydrogen on carbon 3 because it's not just a hydrogen there, it is a methyl group coming off because it's a carbon there. So there's 3 hydrogens coming off of the end carbon. Butane, so but is 4. Same idea, we're going to have our terminal hydrogen connected to our triple bond. This is carbon 1, carbon 2, drawing it linear. Oops, we'll go back to purple here. Drawing it linear, we're going to have carbon 3. And then now adding our next carbon, because we're just going to be adding a single bond, sp3 hybridized, we go back to that zigzag branching that you learned originally when drawing molecules using line bond structure. So our next one would go like this. So we have a CH2 at 3 and then a CH3 at carbon number 4. It's just important that we show the linear part right here. So make sure that you practice drawing and counting your carbons of alkynes so that you don't accidentally put extra carbons in there or lack carbons where you need them. First, let's go through some basic nomenclature rules, and then we'll look at some newer things to consider after. These rules should seem very familiar to you because they're very similar to what we learned for alkenes. So for alkynes, number 1, first, as always, identify the longest continuous carbon chain that contains the triple bond. So it's got to contain the triple bond. This is going to be our newest high priority functional group. And we're not really mixing too many functional groups just yet. Like we haven't learned alcohols or carboxylic acids or anything else. So as of now, the triple bond takes priority in our mind. This is going to be our parent chain. And so we're going to use that suffix that we talked about, "-ine," for our parent chain. And remember to check around kinks and bends and turns. Don't just look at the first straight chain that you see. It can bend around when you're figuring out the longest one. And then you want to begin numbering at the end nearest the triple bond. The triple bond will represent the alkyne, and that has to have the lowest number possible. So for example, if we have this molecule here, and we want to name this, we're going to number, and we're going to start, it looks like on the left, because that will give us the lowest number for our triple bond. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it doesn't matter whether I call up 9 or down 9 because it's the same numbering there, and it's a methyl group. So we have two substituents in this example. We have a methyl group at 3 and a methyl group at 8. So we're still going to put those out front. So we would have 3, 8 dimethyl. Don't forget to include di out front. And also recall that you don't use like di, tri, tetra for ABC order. We would still go by methyl if we had multiple substituents. And then next we indicate the position of the double bond. So in this case, the position of the double bond is at carbon number 4. Oh, sorry, the position of the triple bond is at position number 4. So we're going to say 4. And then how many carbons are in our chain? We have 9. We learned the prefix for 9 is known. And then we're going to end with our new suffix for alkynes. Before we would have ended with "-ine" for alkenes, but now we want to say known "-ine." So ending with that correct suffix. The next rule is that the triple bond is present between two consecutive carbons. So if it is identified at carbon 3, for example, then it would be between carbons 3 and 4. That first number indicates the first position where the triple bond is at. So just as we saw actually in the previous example, that number needs to appear before the parent of the compound that we're naming. So let's do another example here, a couple more practice problems. So if this was our molecule that we're going to name our alkyne, we are going to want to start numbering from the left-hand side. So we give our triple bond the lowest number possible. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That would be our longest chain. And 11 is un dec. And then we're going to have "-ine, so un dec "-ine for indicating that we have a triple bond. This rule is saying that, hey, the position is at number 4, so we throw a 4 out in front of our un dec "-ine, and 4 tells us that that's where the "-ine is at, the triple bond. So what are our other substituents? At 7, we have isopropyl, which goes by I, and at 8, we have ethyl, which goes by E. So our full name here is going to be 8 ethyl, 7 isopropyl, and isopropyl is not hyphenated, which is why ABC order it goes by I. And then ending this, we have 4 as our position of our triple bond, and then 11 carbons, un dec, new suffix is "-ine, so 4 un dec "-ine. If the triple bond is equidistant from either end, begin numbering the molecule at the end nearer the first branch point or first substituent. So if we have this for an example, so if we count from the left or from the right in our numbering, we are going to have 4 as the number for our triple bond. Now, if we were to go 1, 2, 3, 4 from the left, our first branch point would be at position number 3 with the bromo. And if we were to go from the right, 1, 2, 3, 4, our first branch point is at position number 2 with the methyl. It doesn't matter that bromo comes first in ABC order. That would be the next thing we would consider if we didn't have position number 2 with a substituent, or if there was a tie to break. So we are going to go with the red numbering, not the blue numbering, because that gives us the lowest substituent. So continuing them, we're going to have 5, 6, 7, 8. So now when we list the full name, we do list them in alphabetical order, but it's important that we first get the correct numbering down. So we're going to have 6 bromo, 2 methyl, indicate the position of the triple bond, which is at number 4. I must like number 4. So 4, and then we have 8 carbons in our parent chain. That's oct, and our suffix is -ine, octyne. So we have 6 bromo, 2 methyl, 4 octyne. Sometimes you will have molecules that have multiple triple bonds in them. In that case, we use the appropriate Greek prefix to indicate how many triple bonds there are. So for example, if you have 2 bonds, that's a diine. If you have 3 triple bonds, that's a triine. So we throw that Greek prefix in out front. So let's look at an example here. So if this is our molecule, first we want to number it correctly, but we can see that there's 2 triple bonds present. So to give our triple bonds the lowest numbers possible, we're going to start numbering on the right-hand side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 carbons, that's going to be undec. And our ending is going to end up being diine. So the di getting thrown out in front tells the reader that there are 2 triple bonds there. So let's put our substituents out front first. We have at position number 5 an ethyl group, and at positions 6 and 9 we have 2 methyl groups. So putting that in alphabetical order, we're going to have 5 ethyl, 6, 9 dimethyl, and then just like we would indicate the number of one triple bond, we want to indicate the number of both of them. So 3 to 4, so we say 3, and then 7 to 8. So we're going to have 3, 7, and then undec, and sometimes a vowel is thrown in here to make it easier to say. So instead of saying like undec diine, it's often undeca diine. So the diine matches up with the numbers 3 and 7, so that's where the di part comes in. And then the undeca or undec is because there's 11 carbons in the longest continuous chain. Next, we're going to cover a few special rules for naming a molecule known as an enine. An enine is a compound that contains both double bonds, so alkenes, and triple bonds, alkynes. And so there could be a ratio in the numbers of alkenes to alkynes, and this could be modified just a little bit, but let's just start with a molecule that has one of each. So all of the rules that we learned basically apply so far. Find the longest continuous carbon chain. It's got to contain both the double bonds and the triple bonds though. That's going to be the parent. And then in this case, we want to begin numbering at the end where the first multiple bond pops up. So if it's the double bond that's lower, we number that way. If it's the triple bond that's lower, we number that way, if there is a difference between them when we're counting. So let's look at an example here. So if we have this molecule, you can see there is an alkene and an alkyne in it, one of each. And so if I start numbering from the right, I'm going to have higher numbers for both my alkene and my alkyne. Whereas if I start numbering from the left, they're both going to be at lower numbers. So we're going to number from the left because there is a difference. So 1, 2, 3, 4, 5, 6, 7, 8, and then we want to go up this group, 9, 10. So 10 carbons in the longest chain, so that's going to be dec, indicating 10. And at position number 2, this is where we have our alkene. So this is going to be 2En. I'm just going to make a note, and we'll talk about this in a second. Normally we would have ENE as our suffix for alkenes, but we actually don't end up including that final E, and you'll see why. And at position number 5, that's where we have our triple bond, so that's 5YNE, 5I. So those were the suffixes we learned for alkenes and alkynes. So next, anything else we would do is just, take our substituents, put them in alphabetical order out front. None of that changes. So listing that first, we're going to have 4-bromo, 3-chloro, 8-methyl, and then later we'll come back and we'll determine if the double bond is E or Z. And we will throw that out front in parentheses like we did. So we're going to have 2 either E or Z for our alkene. We don't assign E or Z for a triple bond because it's linear. So now to finish this off, what we do is we indicate first the double bond in the name, and then we end with the triple bond. So regardless of the double bond getting a lower number or the triple bond getting a lower or higher number, we still indicate the double bond in the name first and the triple bond at the end as the final suffix, which is why we end up dropping this E right here at the end of alkene, because we're going to end the name with alkyne, and so that's going to bear the final E in the total name that we put together. So after 8-methyl, we would say -2, and then we had 10 carbons. This would be dec, and then we say N. The 2 indicates that the N is where the double bond is at. It's not ene, it's N. And then we put -5-ine. The 5 tells us the position of the triple bond, which ends in -ine. So we only have that E at the very end for the alkyne when we're naming an enine. We don't have it at the end for the alkene. We drop it. And then lastly now, don't forget about putting your E or Z out front in your final name. So going back to position number 2, we want to look at where our high priority groups are. So coming off of position number 3 and number 2, if we look at 3, we're going to have carbon we come to, or we're going to have chloro we come to. So chloro is a higher atomic number. That'll be your high priority group. And then off of position number 2, what's not being shown is there's a hydrogen versus a methyl group. So the methyl group will be your high priority group. So the high priority groups are on Z same side, so it's going to be 2Z in this case. So the full name is 2Z, 4-bromo, 3-chloro, 8-methyl, 2-dec-N, 5-ine. If you run into a situation where the multiple bonds, meaning the double bond or the triple bond, are equidistant from either end that you count from, then we do give priority to one of them, and we give priority to the double bond. This doesn't change the order that we put things in for naming, it's just for numbering. So for numbering, we go with the double bond if there is a tie. That's the only time you use this. Otherwise, you just give the lowest numbers possible. So let's practice and also throw a couple review things in there so we can tie it back to what we did last chapter. You could also start seeing some stereo centers mixed into your molecules. So notice how on the bromo that's being drawn on a wedge. So we have a double bond in this molecule, a triple bond, we have E versus Z for the double bond, and we have a chiral center that's being indicated where we're going to have to determine R versus S in the name as well. So the new rule here is for the numbering. Let's get that down first. Notice if you number from the left or the right, the double bond turns up at position 3 or the triple bond turns up at position 3. So this rule is saying that the double bond is going to get the numbering priority to break the tie. So we're going to start on the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now that we have our numbering down, let's look at what our substituents are. We have a fluoro at 4, an ethyl at 5, and a bromo at 10. So putting those in alphabetical order, we're going to have 10 bromo, 5 ethyl, 4 fluoro, that's FLUORO, and then now we're going to indicate our position of our triple bond, or sorry, our double bond in our name. We have 11, which is un dec. So where's our triple bond? It's at 3. Our double bond's at 3, En. Our triple bond is at 8, Yne. So remember, there's no E here after the double bond. We drop that. So we're going to have 3 un dec N, 8 Yne, so 8 Yne. 3 tells us the position of the double bond, 8 tells the reader the position of the triple bond. So we're almost there. The last thing we're going to do is put a couple of things out front to talk about the stereochemistry. So stereochemistry goes out front. And we have 2 things to indicate out front this time. And they just go in order. So 3 is either going to be E or Z, and 10 is either going to be R or S. So we have parentheses. Now looking at the double bond at position number 3, our high priority group on this side is going to be fluoro, because that has a higher atomic number than carbon. And then on this side you have hydrogen versus this ethyl. So the ethyl is going to be the higher priority. So we have both the high priority groups on the same side. So this is going to be 3Z. And then going over to position number 10, we're going to want to figure out if it's R versus S. So for this one, the hydrogen is already pointed in the back, which is good. We don't have to do a single swap. So bromo is going to be the highest priority group, so we're going to give that 1. To the left, where we have the triple bond, is where the second highest priority group would be, and the methyl would be the third highest priority group. So when we go from 1 to 2 to 3, what direction is our circle going in? It is going counterclockwise, so that would indicate that it is S. So we have an S at position number 10. So when you write the full name, you have to include all of these things that we've already learned and talked about. So 3Z, 10S, that's our stereochemistry out front in parentheses, hyphen, 10 bromo, 5 ethyl, 4 fluoro, 3 undecane, not undecene, and then 8 yne. So including the E on the final alkyne there in the name. The last rule that we're going to throw in for naming enines is, just like we saw when we had multiple bonds for alkynes, you can have multiple bonds for enines. So really you could have any combination of double bonds and or triple bonds. So if you have 2 double bonds and 1 triple bond, we would use the appropriate Greek prefix. We would put 2 out in front of the double bond, so those would be di-N-ines. So di for 1 double bond, just yne for 1 triple bond. For another example, you could have 1 double bond and 2 triple bonds. So in this case, those would be N-diines. So notice it's just N, no ene, and then di indicates 2 triple bonds. Or maybe you have 2 of both, 2 double bonds and 2 triple bonds. You'd have di-N, di-ines in the name. So these aren't the full names. This is just kind of showing you how the ending would change when you use the appropriate Greek prefix to indicate how many of each bond there are. So we'll do one more example here. All right, so we can put together a couple rules that we've already talked about in order to number this and name this molecule correctly. So notice that if we were to start on the left or on the right, we would be at position number 1 for our double bond or for our triple bond. First, remember that the double bonds get the priority, so we're going to start numbering from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 carbons in our longest continuous chain. That's going to be dec. We have 2 substituents to take care of. We have a methyl at 5 and a methyl at 8. So we're going to have 5,8 dimethyl. And when we're looking at our stereochemistry, notice that one of our alkenes is terminal. We do not have E or Z for a terminal alkene because what's coming off of the end right here, we have 2 hydrogens. So there is no difference in priority, so we don't call terminal alkenes E or Z. So the only one we have to worry about our stereochemistry for is between carbons 3 and 4. So we'll come back to that at the end. I tend to just do my stereochemistries at the end after I name it. So now we want to put our positions of our double bond first. So after our 5,8 dimethyl, we have hyphen, we have a double bond at 1, and we have a double bond at 3. So 1, 3, dec, the deca tells us 10 carbons, and that A is just kind of thrown in there for a way to say it easier. And so this is the example of the di-N di-ines because we have 2 double bonds, 2 triple bonds. So deca di-N, remember the 1, 3 matches the di-N there. And then hyphen, where are the positions of our triple bonds in this one? They are at 6 and 9 in this molecule. So 6, 9, and then we're going to have di-ine. So 6 and 9 are where those triple bonds live, those alkynes. And so in this case, we have di-N and di-ine. So those Greek prefixes right there could change di, tri, etc., depending upon how many you have in the overall molecule. Now for our double bond between 3 and 4, remember if we break that in half, we're looking for the high priority groups. Well, here on this side is just a hydrogen that's unwritten, and on this side it's a hydrogen that's unwritten. So since hydrogens are on opposite sides, the other high priority groups, which are the actual R groups, must be on opposite sides as well. So this is going to be 3E because our high priority groups are on opposite sides. So this whole thing would be a priority group, and then this whole thing would be the other high priority group because hydrogens are going to be the lowest priority thing that you can see.